I wanted to slow down and go over number 57 pretty carefully because I think there's a lot of confusion out there about what an implicitly defined function is. You know that I'm a big fan of knowing the difference between an algebraic equation and a function, and too often instructors and textbook authors are not clear about the distinction between functions and equations when they're talking about implicitly defined functions. So let's talk about it. I'll hope to clear it up. I'm going to define a function through an algebraic equation. Okay, the function I'm going to name f. So to specify what f is, I'm going to specify its rule of correspondence. The rule of correspondence will be described this way. Let f be the function that assigns to an ordered pair of numbers x, y the number z such that xy plus z to the third x minus 2y z is equal to 0. Now, the idea here is if we could rearrange this equation to isolate z, this would be a rather strange way to describe this rule of correspondence. If we could algebraically rearrange to put z on one side of the equation and everything else on the other, then that everything else on the other is what we would use to describe the rule of correspondence, right? We would never have to make reference to a symbol z even. We could just erase the left half of the equation, z is equal to all the other stuff. Just get rid of the z symbol, and that other stuff, right, that expression in just x and y would be a description of the rule of correspondence of the function. But I don't know how to do that for this particular algebraic equation. And in general, you don't know how to algebraically rearrange equations in multiple variables to isolate just one. Right? In general, we do not know how to do this. We know how to do it for a small variety of algebraic equations. In a very simple case like this one, it's just not going to be doable. Oh, I don't know, maybe it is doable, but you can imagine in general a case in which it is not doable. I mean, just take x, or I'll write it down here. So take the equation x is equal to y plus e to the y. Can you rearrange that to get y by itself? No, you can't, and nobody else can either. It's really, really easy to come up with equations where you can't do that, okay? So we could algebraically define a function that assigns to x the number y such that x is equal to y plus e to the y, and then we would not be able to give an algebraic expression for f of x. Right? What expression in x would y be equal to? I don't know. But nevertheless, this equation would serve as a perfectly good rule of correspondence. Okay, I'm slowing down a little bit too much. Let me get to the point. Okay, if this function f is as described here, then for all pairs of numbers x, y in R2, we have the following thing. X, y plus, now instead of f, I'm going to write, instead of z, I'm going to write f. F of x and y. Right? And to the third power for that, times x, minus 2y, and instead of z again, I write f of xy. Okay, right? So with f defined this way, this equation is true for all pairs of numbers x and y. All right. Then we have a nice relationship that only involves x and y, and certainly I can take the derivative. I mean, if these two algebraic expressions are equal, then the derivatives with respect to x of both sides are equal. So I will say that implies, the one-way implies, by the way, the partial derivative with respect to x of xy plus f to the third, and just to be lazy, I'm going to write f to the third without an of x and y. You know what I mean. Minus 2y f is equal to the partial derivative with respect to x of 0. Now, of course, the right-hand side of that is 0. And that equation is equivalent to, okay, the partial derivative with respect to x of x times y is simply y, plus, now, the partial derivative of a function to the third power. Well, chain rule, right? 3 times that function squared times df dx. That's simply the chain rule, and I still need to multiply by x. I'm just going to put that over here, that x that I'm multiplying by on the left side, so that df dx is nicely isolated. Minus 2y, let's see, when I'm taking a derivative with respect to x, 2y is a constant, 2y, and then of course the derivative with respect to x of f, I should call df dx. Alright, and that's 0 over there. Now, I can algebraically rearrange this for df dx as a function of x and y, no problem, right? Let's see. I will put the y on the other side with a negative sign, and then I will think about factoring out the coefficients of df dx here and here. Okay, so that I don't confuse too many people, I'm going to do this a little bit slower than I was planning. I'm going to factor out df dx, and the two factors that go with this are 3xf squared and minus 2y. Okay, and that is equivalent to saying that df dx is negative y over 3xf squared minus 2y. Okay. Period mark. You see how I was able to find the derivative of f with respect to x, but I am only able to do it in terms of the function f itself. That is to say, I couldn't find df dx in terms of only x and y. F had to be in there also. Now, your textbook, of course, is not introducing the symbol f, and I think that's the kind of thing that gets people confused about how a function is being implicitly defined and then confused about what implicit differentiation is. Implicit differentiation is, of course, a differentiation of an implicitly defined function. Your book would prefer you, apparently, to write that dz dx is negative y over 3x. Now, remember how I replaced z with f, because that's how the function was defined, right? F of xy is z, such that z makes this equation true. So I am going to go the opposite direction and replace f with z. Z squared and minus 2y. Okay, so once again, the derivative of z with respect to x is being found in terms of y, x, and z itself. Okay, so let's see, i.e. id est. Okay, so I hope that that clarifies for you some ideas about what implicit differentiation is all about, and I hope it enables you to do the rest of these, and I hope that you're having a nice day.